Hello students, in this video we're going to discuss Chapter 13, Queuing Analysis. So queuing is basically waiting in line. So there's various elements of a waiting line system that we're going to analyze, basically for the purpose of trying to determine if any improvements can be made to a waiting system in order to make some of the characteristics, elements better, more effective, more efficient. So elements of the waiting line system form because, as it says there, people or things arrive at a service rate faster than they can be served. Most operations have sufficient server capacity to handle customers in the long run. Customers, however, do not arrive at a constant rate, nor are they served in an equal amount of time. So those are some of the elements of our waiting line or queuing analysis. Waiting lines are continually increasing and decreasing in length and approach an average rate of customer arrivals and an average service time in the long run. And that's a key factor to consider. We're talking about long run averages in terms of arrival and service rates. Decisions are based on those long-run averages, and we're going to use some of those variables to help us decide just how efficient a system is. I think we've all been involved in waiting, whether it be at a bank, retail, hospital, Tim Hortons, McDonald's, wherever. There's always a system in which we are waiting. We're going to analyze those systems. The drive-thru at Tim Hortons, for example, is one. Sometimes it's busy, sometimes it's not so busy, but on the long-run average, there is a known arrival rate and a known service rate. So the first model we're going to look at is a single server waiting line system, and there's some variables that we're going to use to determine just how effective and efficient that system is. Components of a waiting line system include arrivals in terms of customers, servers, cash register operator, someone helping us. Customers in line form that waiting line versus customers in the system. Factors to consider in analysis, we'll talk about each of those in the next slide. We have the queuing discipline, the nature of the calling population, where the customers are coming from, the arrival, and the service rate. So we look at the example that's in your textbook, the fast shop market waiting line system. We have customers on the outside, known as the calling population. They're the source of customers. Customers arriving, the arrival rate, customers being served, the service rate, and customers in line or in the queue, and then customers, the total number of customers in the system. So some of the components, we got the queue discipline, the order in which waiting customers are served. We might think it's first come, first served, but in some systems it's not. Some systems like the emergency room at the hospital is not first come, first served. There's a system in which they prioritize which patients are going to be seen first. Calling population, the source of customers, whether it's infinite or finite. The arrival rate follows a Poisson distribution, and the service rate follows an exponential distribution. So assumptions of this basic single server model: the population is infinite. It is a first come, first served queue discipline. Has a Poisson and exponential arrival and service times. The symbols, there's only two symbols that we're going to use, is the arrival rate, the average number of customers in the long run that arrive per specific time period, and the service rate in the long run, the average number served in a specific time period. We have to make sure that the time periods we're talking about for both arrival and service rates are the same. Customers must be served faster than they arrive. Lambda, the arrival rate has to be less than the service rate, mu, the service rate. Or if it's not the case, then there is an infinitely large queue that will build up. The line will just keep on getting bigger and bigger. So there are 5 or 6 different formulas we look at, and you can see that they all look or use lambda and mu. So one of the key ones, I'll go over the ones that we're going to use in our queuing analysis. The probability that no customers are in a system is p sub 0 is 1 minus lambda over mu. We're going to look at the average number of customers in the system, known as L, which is lambda over the difference between mu and lambda, and the average number of customers in the waiting line, LQ, and it uses that formula. We're not going to be too concerned with the probability that there are n number of customers in the system. So there's 3 out of those 4 listed there that we're going to look at. The average time customer spends waiting and being served is known as W. The average time customer spends waiting in the queue is WQ. And the utilization factor, known as U, is lambda over mu. The probability that the server is idle is just 1 minus the utilization factor. So those are some of the common formulas we use. We're going to look at this example where there are 24 customers arriving per hour at a checkout counter and 30 customers per hour that can actually be checked out. So of course mu is greater than lambda, so it means that this system is not going to get infinitely large. So we want to calculate the following: probability of 0 customers, the average number of customers in the system and in the waiting line, the average time in the system per customer, and the average time in the waiting line, as well as calculating the utilization factor. Now what I would do is I would use Excel help us go through this. What I've done here, we have lambda, we have mu, 24 and 30, that's based on our example here. And then I have created these, the spreadsheet to calculate the various values that we need. Probability of 0 customers in the system is 1 minus lambda over mu, 20%. So the 20% chance that there's no one in the system. So 20% of the time your workers are there without serving anyone, and they could use that time to doing other things. The average number of customers in the system is LQ, being the average number of customers in the waiting line, 3.2. The average wait time in the system, 0.16 hours. And WQ, the average time in the waiting line, is 0.133 hours. Utilization rate, the percent that it's busy, is 20%. So we can calculate it for time, the amount of time in minutes. So the average time in the system per customer is this value, 0.167 times 60. We get 10 minutes. Same thing for WQ, 0.133 times 60 gives us 8 minutes. So on average, long run average, customers waiting 8 minutes in the waiting line. I don't know about you, but that is a long time. 8 minutes. Oof. So let's take a look at some alternatives. That's basically what this chapter is about, trying to determine if there's a benefit, overall benefit in having and making changes to our system. So the first one we're going to look at is various alternatives here. Oops. Alternative 1, addition of an employee raises the service rate from 30 to 40 customers per hour. So basically alternative 1, if we look back at this model here, the new employee is working with the single server, perhaps helping customers bag their items or helping the customers display their items to be checked out. So basically that new employee is helping the single server cashier. So let's look at what this would mean. So all these formulas have been entered, and they are correct. So this is alternative 1. Basically, the service rate has been increased. We can serve more customers because we have 2 customers helping. 2 employees, I should say. 1 cashier, 1 employee helping the customers in line. So that can change to 40. We change this to 40 and look at the differences here. The probability that the system has 0 customers in it has increased from 20 to 40%. Average number of customers in the system is 1.5. Long run average of customers in the waiting line is 0.9. And we got 0.063 hours is the average time per customer in the system. In line it's 0.038. Translating that to minutes, we have 3.75 minutes a customer is in the system, and 2.25 minutes a customer is spending in the waiting line. And our utilization factor is now 60%. So what we can do here is we can determine the overall time difference, basically looking at 8 minutes in the system, 8 minutes in line minus 2.25 minutes. So basically we're saving 5.75 minutes per customer. Now, to fully understand the overall benefit of this is we have to have some marketing research done for us. So perhaps, this is your textbook gets into more detail in this, but perhaps it's known that there is $75 per minute in basic lost sales. So every time a customer goes into a system, looks around going, wow, people are spending too much time waiting to be served, 8 minutes to be exact, I'm out of here. I'm not going to go into that store. Maybe I'll come back later, but maybe, worst case scenario, is I go elsewhere and spend my money elsewhere. So this is something that retail businesses keep track of, potential lost sales, $75 per minute that a customer has to wait. So that is our benefit because we are going to decrease. We're saving time, so basically we are decreasing that lost sales. It does come at a cost. The new employee is hired at $150 per week. So we can take the benefit of $75 times the savings, overall savings, and we will get a benefit of $431.25. So the total savings we have in this alternative is the difference, the benefit because of lost sales minus the cost of the new employee. Basically, we're going to come out ahead by this alternative of $281.25 per week. So this alternative, having an extra worker there, is going to pay off for us. The next video we'll look at the second alternative.